everybody. My name is NARWC Baille. I am a graduate student at Wood School Oceanographic Institution, and this talk will present the work we did with Daniel Zidobart on evaluating the effectiveness of surface-based detection methods for vessel strike mitigation of North Atlantic right whales. The link to our paper's bioRxiv preprint version can be found at the bottom right corner of the slide. The world's oceans have been experiencing an increasing level of use due to growing commercial and recreational activity. In 2020, we were recording close to 800% more vessels traveling the oceans than we did in 1890. The study showed that at least 75 different marine species have had recorded vessel strikes. Species impacted range from large whales to dolphins, seals, penguins, and even fish. As we all know, the North Atlantic right whale is dramatically affected by vessel strikes. It has been shown that they are 2 orders of magnitude more prone to strike than other whale species. This is due mostly to their surface skimming feeding behavior and the habitat and migration routes often overlapping with ports and shipping lanes. Between 1970 and 2006, over 50% of the recorded right whale deaths were caused by vessel strikes. Hence, mitigation strategies are crucial. Here, we define a vessel strike as any physical impact, fatal or not, between any part of a watercraft and a live marine animal. Vessel strike mitigation strategy can be classified into either large or small-scale approaches. Large-scale mitigation strategy establish high-risk areas with specific navigation rules, such as reduced transiting speeds or area avoidance. Such measure may be permanent, seasonal, mandatory, or recommended, and can apply to all vessels or only to a subset. On the other hand, small-scale approaches directly rely on each vessel to detect at-risk animals. Upon detection, they should alter their course and speed to avoid collision. Various methods of whale detection exist, such as radar, sonar, passive acoustic monitoring, human observers, or thermal imaging systems. The aim of this study is to assess the effectiveness of surface detection methods for vessel strike mitigation of North Atlantic right whales, given different vessel and animal characteristics. To this end, we created an agent-based model. In our 3D simulation, named WH World after Whale World, virtual whales and vessels were placed randomly along a grid. They were given a set of characteristics and were instructed to move for an hour so we could observe encounter frequency. Each whale was given a unique artificial dive profile that mimicked true North Atlantic right whale diving behavior. We processed time depth data collected on North Atlantic right whales back in 2000 and 2001 by Mark Baumgartner. Diving behavior were classified as either shallow, deep, or mixed. The shallow mode refers to whales that are surface feeding. The deep mode implies long and repetitive deep dives, and the mixed mode is a combination of both. Characteristic of each mode was extracted and used to create the generated dive profile. Additionally, since exhalation could not be extracted from time depth data, we artificially added a blowing stage, which depicts a whale located at the surface and available for detection. The interval between each series of blow was controlled by the interblow interval parameter, which varied from 30 seconds to 5 minutes, depending on the run. For vessels and detection system parameters, we chose parameters that were broad enough to apply to a wide range of vessel categories. Each vessel has 5 defining parameters: a fixed trajectory, a fixed transiting speed ranging from 1 to 15 meters per second, a 20-degree field of view, which corresponds to the system angle of detection, a fixed reliable detection range, RDR, which is the maximum distance at which a whale blow would still be detected with certainty. And finally, each ship had a reaction time, RT, which is the time needed by a vessel to make effective mitigation maneuvers. This variable integrates covariates such as vessel maneuverability, its ability to slow down, and the time between detection and alert. In the simulation, our surface detection system detects a whale when it is blowing at the surface, within the vessel's field of view, and within a certain distance from the ship. This distance depends on which scenario we choose. In the reliable detection range scenario, the probability of detection is 1 up until a fixed distance RDR. Past that point, it drops to 0, as you can see on the purple curve on the left figure. In the data-driven detection function scenario, or DDF, past the reliable detection range, the probability of detection does not drop to 0, but instead slowly decreases, as depicted by the green curve. This detection function shape was derived from previous experiments and adapted to different RDRs so we could evaluate the impact of various detection system performances as shown on the right figure. Finally, in order to implement successful mitigation, a well has to be detected early enough so the vessel can still take evasive action. To this end, we established a danger and a safe zone. The danger zone is the area where the vessel will be too close to safely avoid a strike if a whale were to be detected there. The danger zone range is directly proportional to the vessel speed and the reaction time. On the other hand, if a whale is detected in the safe zone, vessels will have enough time to implement the necessary measures to avoid a strike. In our study, a whale is detected in time when it was spotted in the safe zone before it enters the danger zone. We define the in-time detection probability, ITDP, as our metric to evaluate the impact of the different vessel and whale parameters. Our study showed that most whale-dependent parameters have a much lower impact on the in-time detection probability than vessel-based parameters. In particular, the top left plot reveals that no difference in ITDP occurred when varying the whale speed. Additionally, the impact from varying interblow interval was only slightly noticeable when testing on higher ship speed of 10 meters per second and longer reaction time. On the other hand, the bottom plot showing ITDP results as a function of whale behavior and ship speed reveals that for low ship speed, whale diving behavior do not affect chances of detection. However, for higher ship speed, above 5 meters per second, the diving behavior of the whale starts to matter. The plot reveals that for a ship speed of 10 meters per second, the ITDP decreases by 25% when comparing shallow and deep diving behavior. This is expected as when a whale goes on deep dive, it surfaces less often, which reduces the chances of detection, making it more vulnerable to strikes. From those results, we can conclude that transiting at low ship speed, such as in speed-restricted zones, helps alleviate the impact of whales' diving behavior. On the other hand, vessel-dependent parameters have proven to be more impactful on the effectiveness of detection systems. As you can see on the top plot, showing ITDP results for varying reaction time and ship speed, if a vessel travels at slower speeds, such as 5 meters per second and under, any form of detection system with at least 1 kilometer of reliable detection range will provide above 90% chances of in-time detection, regardless of the ship's maneuverability. This is a critical finding since it reveals that in slow speed environments, such as speed-restricted zone again, any vessel-based detection system would provide high protection for the animal. On the other hand, the top plot also shows that for higher ship speed, between 5 and 15 meters per second, the ship reaction time and the performance of the detection system start to matter as ITDP results drop for higher RT. The bottom plot compares ITDP results for varying reliable detection ranges and ship reaction time. We can see that for a short reaction time of 1 minute, any ship-based detection system looking at least 1 kilometer away will lead to high ITDP values. However, obtaining such a quick ship response comes with great human efforts and or technological costs, and hence it is unlikely to be implemented on a large scale. On the other hand, the plot also reveals that vessels with lower maneuverability can still have high ITDP values when using larger reliable detection ranges systems that can look several kilometers away. In this bottom plot, we observe a 60% increase in ITDP between a 3-kilometer RDR compared to a 1-kilometer RDR. Such result is particularly useful as it applies to a large group of vessels, such as cruise ships, which have high enough elevation to provide large detection ranges. Hence, vessels with moderate maneuverability can still effectively benefit from onboard detection systems by using a more advanced technology with larger reliable detection ranges, or by simply slowing down. However, the last plot also reveals that vessels which travel at very high speed and that have very poor maneuverability in the order of 10 minutes obtain very poor ITDP results, regardless of the technology used. Supertankers and large container vessels are examples of such ship category. From that, we can conclude that for such vessel characteristics, no currently available vessel-based detection method would provide enough detection range for effective mitigation. To conclude, under the right condition, vessel-based whale detection system can be very effective for whale strike mitigation, and a large-scale deployment of such system at high-risk areas could effectively reduce whale strikes. While certain vessel classes cannot directly benefit from vessel-based detection systems, the information obtained and shared from other vessels equipped with such systems could help estimate a near real-time distribution of whales in critical areas and improve the large-scale dynamic management efforts. With future technological improvement on the hardware and software side, vessel strike mitigation system could become a standard tool in the maritime industry. Thank you.